Hi folks, welcome back to another Cuemath Gems video where we discuss awesome math problems with really elegant solutions. Today's gem is a really cool problem from geometry. This problem is actually from the Cuemath box of math puzzles and it is on this puzzle card that I've taken out. On the back of this puzzle card, you can see the label E6, which means that this puzzle card is meant for Cuemath students between grades 6 to 8. Let me use this cube from the Cuemath math box to help you visualize the problem on this puzzle card. Okay, so imagine that an insect is walking around on this three-dimensional cube. It can walk anywhere on the surface of the cube on any of its 6 faces, but it cannot go into the cube. Now suppose that the insect is at this corner or this vertex of the cube and it wants to walk to this vertex here, the diagonally opposite vertex. Clearly, the insect could take many paths along the surface to go from this vertex to this vertex. For example, it could walk like this, go from here to here, and then from here to this point. Or it could do a longer walk. It could go from here to here, then come here, and then go like this. Or it could even do a zigzag walk. For example, something like this, then go here, and then come here. Now the problem is, what is the shortest path the insect can take along the surface to go from this vertex to this vertex? What is the shortest path the insect can take? Before you go forward, I will really encourage you to pause the video and think a little about how you could solve this problem. Only if you have given it some thought will you appreciate the elegance of the solution. And if you do give it a try, well, you may even crack it on your own. Okay, assuming that you have thought about it, now let me show you a really neat way to solve this problem. To do that, I'm going to use a simulation or virtual model of this cube.
So here's that simulation, which shows a cube with the 8 corners or vertices A, B, C, D, E, F, G and H. I can move this cube around to look at it from various angles, like this. On this cube, suppose that the insect has to go from this starting point A to this diagonally opposite point G. Now I want you to focus on just 2 faces of the cube. The front face AEFB and the top face EHGF. These 2 faces are arranged perpendicular to each other in 3 dimensions, and because of this 3D arrangement, finding the shortest path from A to G is tricky. But let me ask you a question, and I want you to think about this deeply. What if these 2 faces were in the same plane? What if you took the face EHGF and in your mind rotated it so that it comes into the same plane as the face AEFB, like this? Now what is the shortest path the insect could take to go from A to G in this planar or 2D arrangement of faces? Well, the answer to that is super simple. The shortest distance between 2 points in a plane is the straight line joining them. So simply draw the straight line from A to G. This straight line will join A to the midpoint M of the edge EF, and then the straight line will go through to the point G. Now the question is, how does this shortest 2D path help us? Well, if you haven't already guessed it so far, this shortest 2D path is what will also give us our shortest 3D path. How? If you now mentally rotate the face EHGF back into its original position, like this 3D path from A to M to G that we now get is still the shortest path from A to G. And that's because when this 3D path is transformed into 2D, like this, it becomes a straight line joining A to G. So the answer to our problem is that the insect should just walk in a straight line from A to the midpoint of an opposite edge, M in this case, and from there take a straight line path again to B. By the way, this path that you see right now from A to M to G, this is not the only shortest path. In fact, there are 5 other paths like this which will also have the same total length, but I will leave it to you as an exercise to figure out those 5 shortest paths.
What makes this problem a gem is that it seems difficult when you first see it, but you can actually solve it completely in your mind. All you need to do is to mentally transform the original 3D figure into a 2D figure, visualize the shortest path on the 2D figure as a straight line, and then mentally transform that shortest 2D path back into the shortest 3D path. It's like mental gymnastics. Go from 3D to 2D and then back to 3D, and it does not require a single line of calculations. This kind of mental reasoning is something we do extensively at Cuemath because this is what allows students to experience the real beauty of math. If you too like reasoning of this sort, subscribe to my channel and stay tuned for many more such gems.